You're given that the definite integral of f of x from 2 to 5 is 7, that the definite integral from 2 to 7 is 12, and that the definite integral from 5 to 10 is 4, and you're supposed to evaluate different possible definite integrals here. You should be able to use the properties that you know in a formal kind of way, even though we don't have a formula for f of x. So, for example, for part A, you're supposed to integrate f of x from 2 to 10. You've got to use this information in some way. The key thing is to focus on the interval of integration, 2 to 10, and ask, are there any of these given bits of information that will be helpful? We see the integral from 2 to 5 and the integral from 5 to 10. If you want to think of it as area under the curve, we're after the entire area under the curve between x equals 2 and x equals 10. We can use these two bits of information, find the area between 2 and 5, and also between 5 and 10, and add them up. Now, you don't have to give an explanation like that to use this, but I do think it is good to, in your mind, imagine it to help you understand it. Then just use the given information. The integral from 2 to 5 is 7. The integral from 5 to 10 is 4. The final answer is 11. Okay, so it's a fairly straightforward application of the interval property of integration there. Let's skip to part C. Part C is a little bit trickier. In part C, we're supposed to try to figure out the integral from 5 to 7, a smaller interval instead of a bigger one. What should I use? I know the integral from 2 to 7 and 2 to 5. Are those helpful? Yes, but again, it's kind of tricky. The interval from 2 to 7 can be broken up into two pieces, from 2 to 5 and from 5 to 7, based on the integral we're trying to find. So I could write down an equation there, an abstract equation, to say exactly that. The integral from 2 to 7 is the sum of the integral from 2 to 5 plus the integral from 5 to 7. But the integral from 2 to 7 is not what we're after. We're after the integral from 5 to 7 in part C. But it's just a matter of solving for the unknown. Plug in the numbers you do know. You do know the integral from 2 to 7 is 12. The integral from 2 to 5 is 7. And the unknown integral can now be solved for by subtraction. Subtract 7 from both sides. You can say the unknown integral from 5 to 7 is 12 minus 7 is 5. Okay. You also could, right at the start, solve this equation for the unknown integral. You could subtract the integral from 2 to 5 from both sides. You could write that integral from 5 to 7 as the difference of two integrals. The integral from 2 to 7 minus the integral from 2 to 5. And then plug in the numbers. Either way you do it is okay. And on a test, you should be flexible and be able to do it either way. You should be able to solve a problem like this. Part D, it's a little tricky because you got the plus 1 in there. Integral from 2 to 5 of f of x plus 1. First step is to use a linearity property of integrals. You've got the integral of a sum. That's the sum of the integrals. Integral of f plus the integral of 1. That's a little strange. Integrate 1? Yeah, maybe a bit strange, but certainly doable. Think about this graphically. 1 is a constant function. You're integrating from 2 to 5. You're going to find the area of this rectangle. Base is going to be 3. Height is going to be 1. This integral is going to be 3. This integral is one of the given ones. That's 7. So the answer is 7 plus 3 is 10. Right? Do you have to draw pictures? No. It's helpful here. You also could use the fundamental theorem of calculus for the second integral if you prefer. You also could say, what's an antiderivative of 1? X. I could write that integral as x being evaluated from 2 to 5. Plug in 5, subtract what you get when you plug in 2. 5 minus 2 is 3 would be another way to do that integral. that make sense? But you should also be able to show your work in these kinds of ways. You should feel comfortable with that. I didn't have time to talk about average value during class last Friday, but it did come up on the homework. It is just a formula in the book that you can use, but I do know from experience in teaching the class that many people don't really know what to do when they are asked to find the average value of a function. Let's think about average value in the context of problem 55, or 53, excuse me. And this thing's kind of in the way here. There we go. A bar of metal is cooling from 1,000 degrees Celsius to room temperature 20 degrees Celsius. The temperature H of the bar T minutes after it starts cooling is given in degrees Celsius by this formula. Part A says find the temperature of the bar at the end of 1 hour. Part B, okay, that says average value. Find the average value of the temperature over the first hour. And evidently C is about interpreting and explaining why one answer is bigger than the other, or, well, why is your answer to part B is either greater or smaller than the average of the two temperatures at the beginning and the end of the hour. I'm going to go ahead and graph this function right away, even though they don't say that to do that until part C. Think about this here. You've got 20, a constant function, and then an exponential decay, 980 plus or times e to the negative 0.1t. If you didn't have the 20 there, that would be a typical exponential decay looking like this and heading toward a horizontal asymptote at 0 as t goes to infinity, right? Exponential decays. 20 just shifts that up by 20 units. The graph of this is an exponential decay shifted upward by 20 units. Pretend this is 20. It's going to have the horizontal line at 20 as a horizontal asymptote. Its value at t equals 0 is 1,000. 20 plus 980, e to the 0 is 1. So this graph's not really to scale, but humor me, pretend this is 1,000 right there. The scale's wrong. Okay. This is h as a function of t. As far as part A goes, finding the temperature after 1 hour, let's pretend 1 hour is right there. You're trying to just find the y coordinate or the h coordinate at that point right there. Just plug in t equals 1. You don't see function notation here? Okay, you could give this a function name. You could call it f of t, or we could be like a scientist here and be sloppy with our notation and write h equals h of t. You'll see that in science classes. They will use the same letter for both the dependent variable and the function name. The main thing is don't let it bother you. Okay, it's bad notation. It's actually even has an official name. It's called abuse of notation, not abusive notation, but abuse of notation. I am abusing notation there in using the same letter for both the dependent variable, which is a number, and the function name, which is not a number. H as a function name is not a number. It's a function name. That's what it is. Be more typical for us to call that f. But we'll be sloppy here just to help you realize that, yes, sometimes people are sloppy. After 1 hour, that's h of 1. 20 plus 980 e to the negative 0.1. 980 times e to the negative 0.1 is not much less than 980, 886.74, I mean, on the scale. Question? Oh, is t in minutes? Okay, I'm sorry. T is in minutes, so yes, cross that off. It's going to have cooled a lot more. This t is in minutes, and we're talking about 1 hour later, so 60 minutes. Thank you. 60 times negative 0.1 is going to be negative 6. And this will have cooled down quite a bit after 1 hour. 980 times e to the negative 6 is pretty small on a relative scale compared to 980. add 20. It's cooled down quite a bit. It's at 22.4 degrees after 1 hour, which would be 60 minutes. And I should really mark that with a 60 there. Okay, this graph's not accurate then. Okay, maybe that is a 1 or 2 or a 10 or whatever. After 60 minutes, it's not much higher than 20. Part B says, find the average value of the temperature over the first hour. Well, how do you do that? The formula is an integral. It involves an integral. At least it doesn't equal an integral. It equals an integral divided by the length of the interval. The average value of a function f over a closed interval from a to b is 1 over b minus a times the integral, not the integral itself. Yes, you could think of that as 1 over b minus a times the integral. You could also think of that as the integral divided by b minus a. Either way is okay. It's the same thing. Dividing by a number is the same as multiplying by the reciprocal of the number. In our case, we're trying to find the average value of h over the first 1 hour, which is 60 minutes. Yes, t is in minutes. So instead of doing 1 minus 0 on the bottom, I should do 60 minus 0. Integrating from 0 to 60. 20 plus 980 e to the negative 0.1 t dt. That's the integral to compute. Use the fundamental theorem of calculus, right? You have to do that here because you can't think about this area in terms of areas of rectangles or trapezoids. You've got to use the fundamental theorem of calculus. You need an antiderivative of this. Okay, that's a little tricky. Antiderivative of 20 would be 20t. That one's not too bad. But what about this one? Takes a bit of guesswork. It's got to involve e to the negative 0.1t, doesn't it? It wouldn't make any sense to guess a cosine or a sine or a t squared or something like that. The trickiest part is what constant goes in front of it. And enough trial and error reveals that negative 980 over 0.1 is the constant that you want. Why? Check it by differentiation. If you differentiate this, the chain rule gives you an extra factor of negative 0.1, which will cancel with this minus divide by 0.1. You can always check it by differentiation. This is getting evaluated from 0 to 60. Keep that 1 over 60 in front. 20 times 60 would be 1200. 980 divided by 0.1 is 9,800. E to the negative 6 is what you get when you plug in t equals 60. Then subtract what you get when you plug in t equals 0. 20 times 0 is 0, but e to the 0 is not 0. We're going to get a minus 9,800 e to the 0. E to the 0 is 1. This is another minus 9,800. Be careful with your signs. Ultimately, you're subtracting a negative, so you really end up adding 9,800. So you get 1 over 60 times 9,800 plus 1,200 is 11,000 minus 9,800 e to the negative 6, if I have not made a mistake. But look at the people. Hoping I haven't made a mistake. All right, sometimes this happens with integrals. Things are complicated. Do the calculation here. 11,000 minus 9,800 times e to the negative 6 is that. That's got to get divided by 60. 182.93. Did you get that? Does that look right? 182.93 is the average value. It's got units. The units are the same as the units for the dependent variable, h, degrees Celsius. It's an average temperature. It's got to be in degrees Celsius. Does that make sense based on how I talked about units for integrals last time? Yes, if you also take into account the units for the fraction. Remember, the units for the integral are the units for f of x times the units for x. If you pretend this is a multiplication, even though it's not really, it's helpful for intuition and also figuring out units. The units for our f of t function here were degrees Celsius. The units for t is minutes. This is a bit strange. The units for the product would be degrees Celsius times minutes. Yes, you heard that right. Degrees Celsius times minutes. Doesn't make much sense until you realize that since we're also dividing by 60 minutes, the minutes cancel. The integral symbol itself doesn't affect the units because that's like analogous to a summation. You're adding up a quantity. These products, so to speak, are in degrees Celsius times minutes. Adding those up still gives you something in degrees Celsius times minutes, but then dividing by minutes makes the minutes cancel. The units for the b minus a are the same as the units for t, in our case, minutes, leaving you with units of degrees Celsius. And yes, this is smaller than the average of the extremes. Average of extremes, h of 0 plus h of 60 divided by 2 would be the average of the two extremes. 1000 was the temperature at time 0. 22.4 degrees Celsius was the temperature at time 60 minutes. Divided by 2. 1022.4 divided by 2 is 511.2 degrees Celsius, is the average of the two extremes. But the actual average temperature is smaller. Why? Think about it graphically. It's related to the fact that this graph's concave up. This graph here is concave up. Because of that, it spends most of its time, so to speak, in the lower regions where the temperature is relatively low. The temperature decreases pretty rapidly at first. Then when you're over here getting close to t equals 60, the degree decrease is not as rapid. By the time you reach t equals 30, it's pretty low overall compared to 1,000 at least. You're in pretty low temperatures even by the time you reach t equals 30. It's spending most of the time in relatively low temperatures. That's the intuition for why on average, the average temperature should be less than the average of the extremes. The average of the extremes, the average of 1,022.4, that would be 22.4, is halfway between those numbers, somewhere around there, 500 something. But again, our temperature, because this graph's concave up, spends most of the time in the lower values. So the overall average temperature over the entire hour is lower. Here's a precise way to interpret average value. Our average value is 182.93. Pretend that's right here. And again, everything is not to scale. Pretend that's right there, 182.93. Average value is defined in such a way that the area of this rectangle right here that I'm drawing is supposed to be the same as the area under the curve. Why is that? Take a look at this equation. That's the definition of average value. If you multiply both sides by b minus a, you get that the average value times b minus a is going to equal the integral. All I did with there is took the definition of average value and multiplied both sides by b minus a to get that. Integral is the area under the curve. That product is the area of a rectangle. Base is b minus a, height is average value, exactly what I drew. Base is from 0 to 60 in length. Height is the 182.93. That's the area of a rectangle. The average value is defined so that the area of this rectangle equals the area under the curve. Now, you might not think this is a real big deal, but let me tell you, when you get to multivariable calculus, especially, doing double and triple integrals and line integrals, maybe you even learned about line integrals in Gen Physics 2. Maybe a few of you are in Gen Physics 2. Or, well, no, I guess it's Gen Physics 1 now, I guess. Sorry. I was forgetting we're in the fall, not in the spring. When you get to Gen Physics 2, you're going to be doing something called line integrals for electromagnetism and surface integrals. Average value is not really so much a calculation tool there as it helps you understand what the integral means. That's especially relevant in multivariable calculus and its applications. Okay, so this is something worth remembering. I'd like to consider a few problems that I actually did not assign, but I put these on tests before, so I think it would be worth looking at. Testing your understanding of these ideas. I'm thinking of problems 61 through 64 here. So you've got this graph. I will redraw the graph. Like this. Here's A, here's B. You can see this graph is increasing in concave down. It's a graph of some function f of x. Part A says, first of all, draw a length representing f of b minus f of a. You don't need any calculus for that. That's something you should have been able to do before this class. Understanding what graphs of functions mean. F of a is the second coordinate of that point. That's f of a. F of b is the second coordinate of this point, right there. A length representing f of b minus f of a. It's that distance right there on the vertical axis. This is f of b minus f of a. No calculus there. We get to calculus. Well, not even in 62. It's the calculus is in 63 and 64. Yes, 62 is related to calculus. It says a slope representing f of b minus f of a all divided by b minus a. We've seen this before, mean value theorem. That's a rise over a run, isn't it? Run is b minus a. That distance right there. Rise is this, f of b minus f of a. If you draw a right triangle in here, it's rise over run for this straight line. A secant line between 2 points in this curve. It's got slope f of b minus f of a divided by b minus a. We start getting into some actual calculus related to integrals and derivatives in problem 63. 63 says an area representing capital F of b minus capital F of a where capital F prime equals little f. The derivative of capital F equals little f, meaning capital F is an antiderivative of little f. Oh, that looks like what you get from the fundamental theorem of calculus, right? Yes, and that's true. Capital F of b minus capital F of a by the fundamental theorem of calculus is the integral of little f over the interval because capital F is an antiderivative of little f. That's essential. So to say an area representing this difference means it's got to be the area under the curve, the green curve between A and B. That area is capital F of B minus capital F of A. But probably the hardest one is 64. A length roughly approximating capital F of B minus capital F of A divided by B minus A, where capital F is an antiderivative of little f. What length? Doesn't that look like a slope instead of a length? Well, that looks like a length instead of an area. It all depends on what these functions represent. This is the graph of little f, not capital F. Yes, this difference could represent a length on a vertical axis if I was graphing capital F, but I'm not graphing capital F. I'm graphing little f. It's derivative. Yes, this would represent a slope of a secant line if I drew the graph of capital F, but that's not what I have. I have the graph of little f. It can represent a length because of the definition of average value. Capital F of B minus capital F of A divided by B minus A is this integral divided by B minus A by the fundamental theorem of calculus. And that's the average value that we were just talking about with the previous example for little f. And that means it's the height of a rectangle where the area under the rectangle or of the rectangle is the same as the area under the curve. So I'm trying to eyeball it. What vertical distance here will bring me to a spot where if I draw a rectangle, actually starting here, starting at A, where the area of the rectangle equals the area under the curve. Should seem like maybe right about here. Will the area of this red rectangle here equal the blue area under the curve? Why did I draw it right about there? Well, partially because I was looking at these two areas here and noting that if I drew a line about right there, that these two areas approximately cancel out. They're approximately the same. Also notice that I drew it a little higher than halfway between these two numbers. Halfway between those two numbers, the average of those two numbers is right about there. My rectangle is a little higher. Why? Because the graph is concave down. So in effect, it spends most of its quote unquote time in higher values than lower values. The average value should be a little higher than the halfway between the extremes. Same kind of principle as the other problem. So yeah, a length representing that would be this length right about there. Approximately that length would be what this quantity equals. Okay, so that's the trickiest part.